Greetings, esteemed colleagues and distinguished listeners. I'm Zaporizhzhia and I present our joint work with Mirzada Mangilda, Yuri Krak, Big a comparison of the effectiveness architectures LSTM1024 and 2D CNN for continuous sign language recognition process. This study is a collaboration among scholars from the Eurasian National University and the Taras Shevchenko National University of Kiev, along with the Glushkov Institute of Cybernetics. Our research focuses on a crucial task in the field of assistive communication technology, continuous sign language recognition. This task is particularly challenging due to the dynamic nature of sign language, which includes complex movements and gestures that vary significantly from person to person. In our study, we investigated two deep learning architectures, LSTM1024 and 2D CNN. These models were chosen for their potential in processing sequential and spatial data. This study of various neural network models, including DNN, CNN, LSTM, and hybrid models, has shown that each has distinct advantages in processing spatial information like images and temporal data like sequences, and they have shown significant promise in improving the accuracy and reliability of sign language recognition systems. Based on this fundamental understanding, our study focuses on a detailed comparative analysis of two well-known neural network architectures, long short-term memory LSTM and convolutional neural network CNN. Lacking a pre-existing database, we created our own dataset by developing a custom application for recording sign language videos. To streamline the data collection process, we automated it using a hand detection model. The recording starts as soon as a hand is identified in the frame and concludes when it's no longer present, allowing for efficient and focused data capture. We employ high-resolution streaming video to enhance detection accuracy, targeting a frame rate of 60 frames per second for gestural words and 30 frames for the finger spelling alphabet to ensure smoothness and minimize latency. We used the MediaPipe holistic model for real-time pose estimation to track key points in each video frame. This setup provided us with the necessary data to enable our models to efficiently process and recognize sign language gestures. The 2D CNN architecture consists of a sequence of convolutional layers for feature extraction and dense layers for classification and incorporates dropout techniques to improve the ability to generalize to new data. It's particularly well suited for static gesture identification due to its ability to extract spatial features from images. Model performance is evaluated using a categorical cross-entropy loss function to minimize the difference between predicted probabilities and true class distributions. We trained the model on our dataset of over 30 million data points across 40 gesture types. Next, we consider the LSTM1024 model, a recurrent neural network specifically designed to handle sequential data. The distinguishing feature of this model is its ability to recognize dynamic gestures. As seen in the architecture diagram below, our LSTM1024 model is built to accept input sequences, process them through LSTM layers, and output classification through dense layers. We trained this model on our dataset, and as shown in the confusion matrix on the right, the LSTM1024 model exhibits high accuracy. Here we show the training accuracy achieved by our proposed architecture on different sign language datasets, including Ankara University Turkish Sign Language dataset for Argentinian Sign Language, and our collected Kazakh Sign Language dataset. As you can see, our model demonstrated exceptional accuracy on all metrics. The second table presents a comparison of the performance of different models on the AUTSL dataset. Among them, our model stands out, achieving 98% accuracy, because unlike other hybrid approaches that combine multiple models, our single model architecture provides high accuracy, which emphasizes its robustness and efficiency. The results of our comparative tests were quite revealing. The LSTM1024 model demonstrated higher accuracy in continuous gesture recognition compared to the 2D CNN model. This finding highlights the importance of choosing the right architecture based on the specific requirements of the given recognition task. Our research not only contributes to the technical fields of machine learning and artificial intelligence, but also has important implications for the development of more inclusive technologies. By improving the accuracy of sign language recognition systems, we can bridge communication gaps for people who rely on sign language, thereby promoting greater inclusivity. That's all. Thank you for your attention.